History of Nginx. Nginx was created by Igor Sisoev, with its initial public release in October 2004. It was developed as a solution to the C10K problem, which refers to the difficulty for web servers to handle 10,000 concurrent connections. Over the years, Nginx has evolved from a web server to a robust, high-performance reverse proxy and load balancer. This command is used to check the version of Nginx that is installed on a system. Since Nginx has been continuously updated and improved since its initial release in 2004, knowing the version can help in understanding what features and optimizations are available on your installed instance. Key features and advantages of using Nginx. Nginx is a highly powerful and versatile web server that offers a multitude of features and benefits for those looking to optimize their web applications or websites. While it is impossible to cover all aspects in a brief introduction, we will highlight some of the key features and advantages that make Nginx a popular choice among developers and system administrators alike. Nginx excels in handling high volumes of concurrent connections with a low memory footprint, making it highly efficient for high-traffic websites. It serves as an excellent reverse proxy and load balancer, distributing traffic to improve web application scalability and reliability. Its asynchronous, event-driven architecture enables serving static content rapidly, further boosting performance. Nginx's configuration syntax is straightforward, making it accessible for beginners, yet powerful for advanced users. It also supports SSL/TLS termination, enhancing security by encrypting data in transit. These features, among others, contribute to Nginx's increasing adoption as a web server, reverse proxy, and load balancer. Basic architecture of Nginx. Nginx is designed based on an event-driven architecture, which enables it to handle multiple connections within a single thread. This architecture makes Nginx lightweight and efficient, especially in dealing with high concurrency, high performance, and low memory usage. Below, there's a simplified representation to understand its architecture. In the configuration snippet, Worker Processes Auto allows Nginx to automatically adjust the number of worker processes based on the available CPU cores. Each worker process is capable of handling thousands of connections due to the efficient use of the events block, where Worker Connections 1024 specifies the maximum number of simultaneous connections that can be opened by each worker process. This setup demonstrates Nginx's event-driven model, where a small number of worker processes can manage a large number of connections, making it scalable and responsive. Differences between Nginx and Apache. Nginx and Apache are two of the most widely used web servers on the internet. They both handle the tasks of a web server, but they do so in different ways that have implications for performance, scalability, and how they are best used. The primary difference between Nginx and Apache lies in their architecture and performance. Nginx is event-based, which allows it to manage multiple requests within a single thread. Apache, on the other hand, uses a process-driven or thread-driven approach, depending on the chosen multi-processing module, MPM, which can lead to increased resource consumption. This architectural difference makes Nginx more scalable and efficient at handling high concurrency scenarios, while Apache's flexibility with dynamic content, due to its extensive module library, makes it highly customizable. Additionally, Nginx is often praised for its reverse proxy capabilities, making it a popular choice for load balancing, whereas Apache's strong suit includes its .httaccess feature, allowing for easy per-directory configurations without server restarts. Installing Nginx on various operating systems, Linux, Windows, macOS. Most Linux distributions support Nginx and can be installed via package managers such as apt for Debian-based systems, yum for Red Hat-based systems, or Zephyr for SUSE-based systems. The commands first update the package lists for upgrades and new package installations. Then, sudo apt install Nginx installs Nginx. Replace apt with yum or Zephyr if you're using a different Linux distribution. After installation, the Nginx service starts automatically. Use sudo systemctl start Nginx to start Nginx if it didn't start automatically. Understanding Nginx configuration files. Nginx, a powerful and efficient web server, utilizes various configuration files to manage its operations, rules, and behaviors. At the heart of Nginx's configuration is the nginx.conf file, which often includes other configuration files to streamline management and organization. Understanding its syntax and structure is crucial for effective web server administration. The code snippet presents a basic structure within the nginx.conf file, defining a server block within the HTTP context. HTTP acts as a container for settings affecting HTTP server functions. Each server block specifies directives for an individual server or website. Listen determines the port Nginx listens on, while server name defines domains. The location/block specifies the root directory for files and the default index files. These directives guide Nginx on how to handle HTTP requests, setting the foundation for serving web content efficiently. Basic Nginx configuration directives. Upon installing and running Nginx, the next critical step is to understand how to configure it. Nginx configurations are stored in a plain text file, usually nginx.conf, and follow a specific structure composed of directives and blocks. Let's delve into some fundamental directives to grasp how Nginx can be configured to handle client requests. This sample configuration defines basic directives within the HTTP context, encapsulating a server block. Listen 80 specifies that the server should listen on port 80, the default port for HTTP traffic. Server name example.com designates the host name. The location/block configures the root directory to /var www.html for requests to the base URL and sets the default index files. These directives are foundational in defining how Nginx responds to client requests, routing them appropriately based on the received URL and method. Managing Nginx service: start, stop, restart, reload. After installing Nginx, it's crucial to understand how to manage its service to ensure your web server can handle requests as intended. The primary commands to manage the Nginx service include starting, stopping, restarting, and reloading the configuration without dropping connections. These commands are vital for applying new configurations, troubleshooting, and ensuring the Nginx service runs smoothly. The sudo systemctl start nginx command starts the Nginx service. Use sudo systemctl stop nginx to stop the service, halting all Nginx operations. To apply changes after modifying configuration files or to restart the service for any reason, use sudo systemctl restart nginx, which stops and then starts the service. If you need to apply configuration changes without interrupting currently connected clients, sudo systemctl reload nginx allows Nginx to reload its configuration files gracefully. All these commands are essential for managing the Nginx service on systems using systemd. Serving static files. Nginx can serve static content, such as HTML, CSS, and image files, directly to clients. Serving static files efficiently is a common use case for a web server. You define where Nginx should look for these files using the root directive. In this configuration, when a client requests htexample.com/, Nginx serves the file located at var index.html or however h.htm, depending on which file exists. The listen directive tells Nginx to listen for incoming connections on port 80. Server name specifies the domain. The location block defines how to respond to requests for the root URL /. The root directive specifies the directory where Nginx should look for the files to serve. The index directive tells Nginx which file S to serve by default when a directory is requested. Configuring virtual hosts. In Nginx, virtual hosts are used to serve multiple websites from a single server instance. These are defined using server blocks within the Nginx configuration file, allowing each website to have its own specific configuration, such as domain names and document root. This is a core feature for web hosting, making Nginx versatile for different web applications. This code snippet demonstrates a basic configuration of a virtual host in Nginx. Here, a server block is defined to listen on port 80, which is the default port for HTTP traffic. The server name directive is used to specify the domain name of the website. The location/block sets the root directory for the website to var/www/example.com, where Nginx looks for files to serve. Finally, the index directive specifies that index.html should be served as the default page when the root of the domain is accessed. Understanding and configuring location blocks. In Nginx, location blocks define how to process requests for specific resources based on their URI. They play a crucial role in routing, applying security policies, and defining how to serve content. Understanding how to configure these blocks is essential for effective Nginx administration. In this configuration, there are two location blocks within a server block, listening on port 80 for example.com. The first location blocks specifies the document root /ww/html, where the server will look for files to serve, with index.html or index.htm as the default files to serve if no file is specified in the URI. The second location block /images/ enables directory listing auto-index for URIs starting with /images, allowing users to see a list of files in the directory if no specific file is requested. Setting up index files and auto-indexing. In Nginx, setting up index files determines which files should be served as the default in a directory, often used for home pages. Auto-indexing enables or disables the display of directory contents when no index file exists. In this code snippet, within the location /block, we're specifying that index.html or index.htm should be the default files that Nginx serves when a directory is accessed. If no such file is found and auto-index is set to on, Nginx will generate and display a listing of the directory's contents. This could be useful for directories you want to be browsable when they don't contain an index file. Error handling with custom error pages. In Nginx, custom error pages allow you to provide a better user experience when an error occurs. Instead of showing the default error messages, you can define your own error pages that match your site's theme and provide helpful information to users. This Nginx configuration snippet sets up a custom error page for the 404 not found error by specifying a path to the custom error page, custom404.html. The error page directive is used to define the error code, 404 in this case, and the path to the custom page. The location block for /custom404.html marks this resource as internal, meaning it can only be accessed internally by Nginx when redirecting for an error, not directly by client requests. This prevents external users from directly accessing the error page URL. Generating SSL certificates. To secure communications between a client and your server, SSL TLS certificates are essential. These certificates are used to encrypt the data transmitted, ensuring privacy and integrity. You might use a certificate authority, CA, like Let's Encrypt for production environments, but for testing or development purposes, generating a self-signed certificate is a quick and straightforward method. Below is the command to generate an SSL certificate using OpenSSL. This command uses OpenSSL to create a new self-signed certificate, nginx-selfsign.c, and the private key, nginx-selfsign.key, for it. .x509 specifies that you want to generate an x509 certificate. -nodes makes the private key not encrypted with a passphrase, which is useful for automated tasks. -days365 sets the certificate's validity for 1 year. -new key RSA 2048 creates a new certificate request and 2048-bit RSA key in one go. You'll be asked to provide information that will be incorporated into your certificate request, such as the country name, organization, and common name, the domain name of your server. It's crucial for the common name to accurately represent the domain name that will be secured with this certificate, especially for production environments. Configuring Nginx with SSL TLS. To secure web communications, configuring Nginx to use SSL TLS is essential. This involves creating or obtaining SSL certificates and modifying the Nginx configuration to use these certificates. This setup ensures that data transmitted between the client and the server is encrypted, providing confidentiality and integrity. This configuration enables SSL TLS for a server block in Nginx. The Listen 443 SSL line tells Nginx to listen for SSL connections on port 443, the standard port for secure web traffic. Server name specifies the domain. SSL certificate and SSL certificate key point to the SSL certificate and key files, respectively. The location directive defines the root directory for the server and the default index files. This setup ensures encrypted communication for users accessing example.com. Redirecting HTTP traffic to HTTPS. Redirecting HTTP traffic to HTTPS is a common practice for enhancing website security. This ensures all communications between the user's browser and the server are encrypted. Nginx can be configured to automatically redirect any HTTP requests to HTTPS using a server block. In the provided Nginx configuration, we define a server block that listens on port 80, which is the default for HTTP. The server name directive specifies the domain name. The crucial part is the return 301 HTTPS/server name request URI line. This tells Nginx to return a 301 moved permanently response to any HTTP request, redirecting the client to the HTTPS version of the URL. The $server name variable uses the server's name, and $request URI appends the originally requested path and query string, ensuring the client is directed to the exact same page on the secure protocol. Securing Nginx with strong encryption settings. To enhance security, it's crucial to configure Nginx with strong encryption settings. This involves utilizing only secure protocols, ciphers, and setting up a robust SSL configuration. The following code demonstrates how to restrict Nginx to use secure TLS protocols and strong ciphers, ensuring your web server communicates securely. The SSL Protocols Directive specifies which TLS versions to support. Here, it's TLS v1.2 and v1.3, which are currently the most secure versions. The SSL Ciphers Directive lists the ciphers the server is permitted to use, selecting only strong cryptographic ciphers for encryption. SSL Prefer Server Ciphers On ensures that the server's preference for cipher suites is prioritized over the client's, enhancing the security by not allowing clients to use less secure ciphers that they might support. Together, these settings fortify your Nginx server's encryption setup against vulnerabilities, ensuring secure communication. Let's Encrypt integration for automated certificate issuance and renewal. Let's Encrypt is a free, automated, and open certificate authority that you can set up on Nginx to secure your website. By leveraging tools like Certbot, you can automate the issuance and renewal of SSL TLS certificates, ensuring that your web content is served securely. This setup enhances your site's security and improves user trust. The provided command uses Certbot, an Acme client, to both obtain a certificate from Let's Encrypt and automatically configure Nginx to use this certificate for yourdomain.com and www.yourdomain.com. It operates by modifying the Nginx configuration files to include the necessary directives for SSL, such as SSL certificate and SSL certificate key. The mash manage Nginx flag specifies that Certbot should automatically detect and modify the Nginx configurations. This automation simplifies the process of securing your website with HTTPS, reducing manual configuration errors and ensuring continuous encryption through automated renewals. Understanding the reverse proxy model. A reverse proxy stands between clients and servers, acting on behalf of clients, usually a web browser, to retrieve resources from one or more servers. These resources are then returned to the client as though they originated from the reverse proxy server itself. The reverse proxy model is beneficial for load balancing, caching, SSL encryption, and more. In this Nginx configuration example, Nginx acts as a reverse proxy. The listen directive tells Nginx to listen on port 80, the standard port for HTTP. Server name specifies the domain name. The location/block routes all requests to the proxy pass specified backend server. Proxy set header directives are used to pass client request headers to the backend server, ensuring the original client IP and other details are forwarded correctly. This setup is fundamental for enabling Nginx to handle client requests and serve content from backend servers seamlessly. Configuring Nginx as a reverse proxy. To configure Nginx as a reverse proxy means setting up Nginx to forward requests for a specific application to another server, typically a backend web server. This setup enables Nginx to handle all incoming network traffic and act as a gateway to your application, offering benefits such as load balancing, caching, SSL termination, and more. This Nginx configuration instructs Nginx to listen on port 80 for incoming traffic for yourdomain.com. Inside the server block, a location block defines a rule for the /path, meaning all requests to your domain. The proxy pass directive forwards these requests to your backend server. The proxy set header directives modify the request headers sent to the backend. Host sets the original request's host. xreal-IP and xforwarded4 provide the client's IP address, and xforwarded proto offers the original protocol, e.g. HTTP or HTTPS. This configuration enables your backend to see the original client requests as if they directly reached, aiding in logging, authentication, and redirection. Reverse proxying to HTTPS backends. When using Nginx as a reverse proxy to secure backend servers, it's crucial to configure it to communicate over HTTPS. This ensures encrypted communication between Nginx and the backend servers, enhancing security by protecting data in transit from eavesdropping or interception. The following snippet shows how to set up Nginx to reverse proxy to an HTTPS backend. This configuration instructs Nginx to listen for incoming connections on port 80 for the domain example.com. For any requests, it acts as a proxy and forwards them to https backend-server.com. It also includes a set of proxy set header directives to forward the original hostname, client IP address, and the protocol used, ensuring the backend server receives these critical pieces of information along with the request. This setup is essential for maintaining the integrity of the original request while securing the data transmission. Load balancing with Nginx. Load balancing is a method used to distribute incoming network traffic across multiple servers. This ensures no single server bears too much demand. By spreading the load evenly, load balancing improves responsiveness and increases the availability of applications. Nginx can act as a powerful load balancer with simple configurations. In this configuration snippet, Upstream defines a group of server backends under the name MyApp. It lists the servers that will receive forwarded traffic. The server block listens on port 80, which is the standard port for HTTP traffic. The location/block catches all requests to this server and uses proxy pass to forward them to our defined upstream group. Nginx will then automatically apply its load balancing mechanism to distribute incoming requests across the servers defined in MyApp. This setup not only balances the load, but also provides a simple failover mechanism, as Nginx will skip over any servers that are down. Handling WebSockets with Nginx. When configuring Nginx to serve as a reverse proxy for a WebSocket application, specific directives are necessary. WebSockets allow for full duplex communication channels over a single long-lived connection, making them ideal for real-time applications. Nginx, by default, doesn't treat WebSocket traffic any differently from regular HTTP traffic, so you must explicitly configure it to properly handle WebSocket connections. This involves setting headers and leveraging certain Nginx modules to ensure the connection is upgraded from HTTP to WebSockets correctly. In this configuration, a map block is used to define a variable connection upgrade that changes the connection header based on the client's HTTP upgrade header. If the client requests an upgrade, Nginx forwards this request to the backend service. The proxy pass directive specifies the backend service to which the WebSocket traffic is sent. Proxy HTTP version 1.1 is essential for WebSockets to function, as it uses HTTP 1.1 for its handshake. The proxy set header directives are used to modify the headers to ensure the WebSocket handshake is recognized and handled properly by the backend. This configuration ensures that WebSocket connections are established and maintained through the Nginx reverse proxy. Understanding Nginx log files. Nginx uses two types of log files to help with debugging and monitoring: access logs and error logs. Access logs record every request made to the server, while error logs capture information about errors that occur during the handling of requests. By default, these logs are stored in /log/nx/, but can be customized in Nginx's configuration files. In the provided configuration snippet, the error log directive specifies the path to the error log file and sets the logging level to warn. This means that messages with a severity of warn and higher will be logged. The access log directive specifies the path to the access log file. The combined option indicates that a predefined format, which includes information such as the client IP address, user identifier, timestamp of the request line, response status code, size of the response body, referrer, and user agent, will be used for each entry in the access log. These directives can be placed in the HTTP, server, or location contexts to control logging at different scopes. Configuring access and error logs. In Nginx, logging is a crucial aspect that helps in diagnosing issues and understanding web traffic. Configuring access and error logs involves specifying where these logs should be stored and what information they should contain. Access logs track every request to the server, while error logs capture any errors encountered. Below is a simple example of how to configure these logs within an Nginx server block. In the given code snippet, two directives within the server block configure logging: access log and error log. The access log directive specifies the path to the file where all access logs should be stored. In this case, var log nginx access.log. Similarly, the error log directive defines the path for storing error logs, here/var nginx error.log. These paths can be absolute or relative to the directory where Nginx is running. By configuring these paths, you instruct Nginx where to save information about every request it handles and any errors that occur, making it easier to troubleshoot and analyze traffic. Log rotation. Log rotation is crucial for maintaining application logs in an efficient manner. Without log rotation, log files can grow indefinitely, consuming significant disk space and making log management cumbersome. Log rotation involves periodically archiving current logs and starting fresh ones. This can be handled externally by tools like logrotate on Linux systems, which can be configured to compress, move, and delete old log files. The provided logrotate configuration snippet does the following. It applies to logs ending with .log in the specified path. It rotates logs daily, keeps 14 archived logs before deletion, and compresses the older logs to save space. Missing OK prevents errors if there are no logs to rotate. Archived logs are compressed, except the most recent one, to facilitate quick access, and access permissions are set with create. The shared scripts option runs the post-rotate script once, using Nginx's signal handling to safely reopen the log files without losing any logs. This ensures logs are managed efficiently without manual intervention. Monitoring Nginx performance. Monitoring Nginx's performance is crucial for maintaining the efficiency and reliability of your web services. By observing various metrics such as request rate, error rate, and response times, you can gain insights into the health and performance of your Nginx server. The stub status module is a valuable tool for accessing basic metrics. It needs to be enabled in your Nginx configuration. Below is an example of how to enable and access these metrics. In the configuration snippet, a new location block is defined as /basic status, which enables the stub status module, showcasing the server's vital metrics. The stub status directive inside this block activates the module. The allow 127.0.0.1 and deny all directives are security measures to ensure that only requests from the local server, localhost, can access this status page. This setup provides a straightforward way to get insights, such as active connections and request processing rates, among others, which are fundamental for monitoring the server's performance. Integrating with external monitoring tools, e.g. Prometheus, Grafana. Integrating Nginx with external monitoring tools like Prometheus and Grafana allows for enhanced visibility into web server performance and health. Prometheus scrapes and stores metrics, while Grafana visualizes them. This requires exposing Nginx metrics to Prometheus format, often through the ngxtp stub status module or third-party modules like Nginx module-vts. This configuration snippet for Nginx enables the ngx score HTTP stub status module at the /metrics endpoint, which Prometheus can scrape. The stub status directive provides essential server status information, such as the number of active connections and requests per second. In a Prometheus setup, this endpoint is added to the Prometheus config as a target for data collection. Afterwards, using Grafana, you can connect to the Prometheus data source and create dashboards to visualize and monitor these Nginx metrics in real time. Conditionals with the if directive. The if directive in Nginx allows for conditional logic within your configuration. It can test variables and execute different directives based on the conditions. However, using if has its caveats and should be used carefully, especially within location blocks. In this code, within any location/block, the if directive checks if the HTTP host variable matches example.com. If the condition is true, it uses the return directive to send a 301 redirect to the client, directing them from example.com to fs/example.com. This is a common use case for if, where you might want to enforce certain policies like redirecting to a www subdomain or HTTPS. rewrite rules, and regular expressions. In Nginx, rewrite rules are used to change parts of a request URI or redirect certain requests. Regular expressions, regex, provide a powerful way to identify patterns in strings, making them ideal for complex rewrite rules. Understanding how to craft and apply these rules is crucial for creating efficient, dynamic Nginx configurations. This snippet showcases a typical Nginx rewrite rule using a regular expression. It targets URLs that begin with /download/, followed by any character sequence, then /media/, a file name, and an extension. The rule transforms these URLs by replacing /media/ with mp3 and changing the file extension to mp3. The last keyword indicates that rewriting should stop here and not apply any further rewrite rules. This rule effectively redirects media requests to their corresponding mp3 versions, demonstrating the power of regex for URL manipulation in Nginx. Using variables and maps in configuration. In Nginx configurations, variables and maps provide a powerful way to dynamically control behavior based on request properties. Variables can be used to store intermediary values, while maps allow the creation of key-value pairs for decision-making processes. Here, we'll create a simple map to change the root directory based on the request's host header. In this snippet, a map is defined within the HTTP block, associating host values with root path values. The hostnames directive enables exact name matching, including wildcards. If the HTTP host matches example.com, the root path is set to varth www.example. This alters the document root dynamically based on the request's host. The default path is used if no matches are found. This demonstrates how maps can simplify configurations by abstracting and reusing logic. Rate limiting to protect against DDoS attacks. Rate limiting in Nginx is a crucial security measure to protect your website against DDoS attacks. By limiting the number of requests a user can make in a given time period, you can mitigate the risk of your services being overwhelmed by malicious traffic. Implementing this requires the use of the limit rec zone and limit rec directives within your Nginx configuration. This configuration sets up rate limiting in two parts. 1. Definition of a rate limiting zone. Limit rec zone binary remote adder zone equals mylimit 10 mega, rate equals 10 r high mer. Creates a zone named mylimit that tracks requests based on the visitor's IP address, binary remote quad adder. It allocates 10 megabytes of memory to store the state of each address and limits users to 10 requests per minute. 2. Application of the rate limit. Limit rec zone equals mylimit burst of 5 applies the previously defined rate limit to requests accessing the /location. The burst parameter allows a user to exceed the rate limit momentarily, by 5 requests in this case, before fully enforcing the limit, thus offering a balance between security and usability. Securing Nginx with basic authentication and IP whitelisting. To enhance the security of your Nginx server, it's advised to implement measures such as basic authentication and IP whitelisting. Basic authentication requires users to input a username and password before accessing your content, while IP whitelisting allows only specific IPs to access your server, providing an additional layer of security. This configuration begins within the HTTP block, defining an upstream with multiple servers, indicating a load balancing setup. Inside the server block, we listen on port 80 for mysite.com. The location /block applies rules for the root URL /. It starts by allowing access only to IPs in the 192.168.1.0/24 range and denying access to all other IPs. This is what we mean by IP whitelisting. Following, auth basic activates username password authentication, presenting users with a restricted content prompt. The auth basic user file directive points to the file nginx.htpasswd containing the valid usernames and encrypted passwords. This setup ensures that only authenticated users from specified IP ranges can access the content. Understanding and tuning Nginx worker processes. Nginx operates with a master worker architecture. The master process is responsible for managing worker processes, which handle client requests. The number of worker processes is a critical tuning parameter affecting Nginx's performance. By default, Nginx may automatically set this number, but configuring it manually can optimize performance based on your server's CPU cores. The worker processes directive in the nginx.conf file specifies the number of worker processes Nginx should use. Setting this to auto allows Nginx to adjust the number of worker processes according to the number of CPU cores available, optimizing resource usage and load distribution. However, this value can be set to a specific number if detailed control over resource allocation is desired. Connection processing methods select, poll, epoll. In optimizing web server performance, understanding how Nginx handles client connections is crucial. Nginx can utilize different methods for connection processing: select, poll, and epoll. These methods affect scalability and performance under various loads. This configuration directive in Nginx sets the maximum number of simultaneous connections that can be opened by a worker process. While select, poll, and epoll are not directly configured here, the worker connections setting is intrinsically tied to the connection processing method's efficiency. Select and poll have limitations on the number of connections they can handle effectively, while epoll, available on Linux, can manage a large number of connections more efficiently. Therefore, the epoll method, being more scalable, is preferred for high-load environments, while select and poll may be used on systems where epoll is not available. Optimizing TLS for performance. Optimizing TLS, transport layer security, in Nginx improves encrypted connections performance, enhancing server response times and security. Key optimization steps include enabling session caching, selecting efficient cipher suites, and leveraging modern TLS protocols. Here's a concise example of how to apply these optimizations in your Nginx configuration. The code snippet does three main things for TLS optimization. 1. Enables TLS 1.2 and 1.3 protocols only, ensuring safer and faster connections. 2. Specifies a list of efficient cipher suites that offer a good balance between security and performance, focusing on ECDHE for key exchange and AES 128 GCM for encryption. 3. Configures SSL session caching to shared, allowing multiple worker processes to share the same session cache, and sets the cache size to 10 megabytes with a timeout of 10 minutes. This significantly reduces the SSL handshake time for returning visitors, improving the overall site performance. Caching content to reduce load. Caching is a crucial technique to enhance the performance of a website. By storing frequently accessed files in memory, Nginx can serve content faster to the users, reducing load times significantly. This tutorial will guide you through setting up basic caching for your website using Nginx. This Nginx configuration snippet enables caching for JPEG images. The location block matches any requests ending with .jpg. Proxy cache specifies the cache zone. Proxy pass defines the backend server address. Proxy cache valid 201D sets cached items with a 200 OK response to be considered valid for 1 day. Proxy cache use stale allows serving stale content if the backend is down or updating, improving the user experience during backend failures. Compression with gzip. Gzip compression reduces the size of the files sent from your server to increase the speed to which they are transferred to the browser. By compressing resources, you can significantly improve your site's load time, especially for users with slower internet connections. In Nginx, configuring gzip compression involves enabling it and specifying which types of files should be compressed. The gzip-on directive enables gzip compression in Nginx. The gzip types directive specifies which MIME types should be compressed. In the example, common file types such as plain text, CSS, JSON, JavaScript, and XML are included. By specifying these types, you ensure that Nginx compresses them before sending them over the network, making your web content load faster for users. This configuration is typically placed within an HTTP or server block in your Nginx configuration file. Setting up Nginx in a high availability setup. In a high availability HA setup for Nginx, the goal is to ensure that the service remains accessible even if one or more servers fail. This involves configuring multiple Nginx servers to work together, often using a load balancer to distribute traffic among them. The example provided here will focus on a simple HA configuration using Nginx as both the load balancer and the web server. The upstream block defines a group of server backends that Nginx will balance requests among. Here, backend1.example.com and backend2.example.com are the backend servers. Next, within the server block, the listen directive tells Nginx to listen on port 80, HTTP, and the location/block configures Nginx to pass all requests to the upstream group named backend. This achieves a basic load balancing setup, effectively distributing incoming traffic between the two backend servers, thereby enhancing the high availability of the system. It's crucial that the backend servers are configured to serve the same application to ensure seamless operation. IP hash and least connected load balancing methods. In the context of high availability and scalability in Nginx, load balancing is a crucial technique used to distribute incoming network traffic across a number of servers. The IP hash and least connected methods are two approaches within Nginx's load balancing toolkit, each serving different purposes and scenarios. This code example demonstrates the configuration for both IP hash and least connected load balancing methods within a single upstream block in Nginx, although in practice, you would typically use one method at a time. The IP hash directive is used to ensure that the requests from the same client IP address are always forwarded to the same server, as long as it's available, which is particularly useful for session persistence. The least con directive instructs Nginx to forward new requests to the server with the least number of active connections, aiming to distribute the load more evenly. It's worth noting that having both directives in the same upstream block, as shown, would not work as intended, and serves here only for illustrative purposes of both methods. Using upstream modules for dynamic scaling. Nginx offers the capability to efficiently manage a group of servers for load balancing through the use of upstream modules. This feature aids in dynamic scaling by distributing client requests among a pool of servers, backends, thereby improving the scalability and availability of web applications. Here, we'll create a simple upstream configuration that demonstrates how to use Nginx to facilitate dynamic scaling. In the given code snippet, an upstream block named backend is defined within the HTTP context of the Nginx configuration. This block specifies a group of server backends that requests can be distributed across. The least con directive instructs Nginx to favor the server with the least number of active connections, contributing to even load distribution and dynamic scaling. Each server directive within the upstream block specifies an individual backend server with options such as max fails and fail timeout configured for one of the servers to fine-tune failure handling. Finally, within a server block, the location block routes incoming requests to the defined upstream group using the Proxy pass directive, thereby enabling dynamic scaling by distributing client requests across multiple servers. Integrating Nginx with cloud services. Integrating Nginx with cloud services allows for enhanced scalability and reliability of your web applications. This can be achieved by utilizing cloud load balancers, auto-scaling groups, and configuring Nginx to work seamlessly with these cloud-native features. Below is a basic example of configuring Nginx to serve as an origin server behind a cloud-based load balancer. In this configuration, Nginx acts as a reverse proxy, accepting HTTP requests on port 80 and forwarding them to a web application running on the same server, localhost, on port 3000. The proxy set header directives ensure that the original request information is preserved and forwarded to the application. This setup allows Nginx to be placed behind a cloud load balancer, which will direct incoming traffic to Nginx based on predefined rules or metrics, thus integrating Nginx into the cloud infrastructure and benefiting from the scalability and high availability offered by cloud services. Best practices for scalability and disaster recovery. Achieving high scalability and efficient disaster recovery in an Nginx environment involves a combination of configuration strategies and architectural decisions. Following best practices is essential for ensuring your web applications are resilient against failures and can handle peak loads gracefully. The code configures an Nginx upstream block to distribute incoming requests among 3 backend servers, introducing both scalability and redundancy. The first 2 servers are standard, while the third one is marked as backup, serving requests only if the primary servers fail. This setup ensures that your application can scale by distributing the load and has a minimal disaster recovery mechanism by automatically redirecting traffic to the backup server in case of failure. Implementing such configurations is crucial for maintaining application availability and performance under varying loads and potential server downtimes. Understanding Nginx modules. Nginx, a powerful and versatile web server, extends its functionality through modules. These modules can be either built-in or dynamically loaded. They provide various features like caching, load balancing, web serving, and more. In this topic, we'll delve into how to view and manage these modules. The command nginx-v displays version and configuration information for the running Nginx instance, including compiled modules. Here, we pipe the output into grep to filter for the start with HTTP SSL module, which is a commonly included module for handling secure HTTP traffic, HTTPS. This serves as a technique to check if a specific module, in this case SSL support, is enabled in your Nginx installation. The presence of this module in the output indicates that HTTPS can be configured and served by Nginx. Commonly used third-party modules. Nginx, a powerful and versatile web server, allows for the extension of its capabilities through third-party modules. These modules can offer additional functionality such as improved security, enhanced performance, or integration with other services. We will explore some commonly used third-party modules to understand their purpose and how they can be integrated into an Nginx setup. This line of code is used to load the GeoIP2 module into Nginx, which is a third-party module. The GeoIP2 module allows Nginx to utilize Maxmind GeoIP2 databases for geolocation features, enabling the server to make decisions based on the geographic location of the client. This could include redirecting users to a localized version of a site or restricting access to certain regions. To use this feature, the GeoIP2 module must be compiled with Nginx, and the load module directive is added to the Nginx configuration file to activate the module. Developing custom modules. Developing custom modules for Nginx allows developers to extend the functionality of their web server to meet specific needs that are not covered by the standard modules. Custom modules can be used to add new features, alter existing behavior, or integrate Nginx with external systems. The process involves setting up a development environment, writing the module code in C, and compiling it with the Nginx source code. The code snippet is a simplified structure of a custom Nginx module. It defines a module with various callback hooks for different stages of the Nginx process cycle, though most of them are set to null here, implying they do not perform any action. This is a template for the Nginx module T structure, which every module must define. The structure includes the module's context, which typically holds pointers to its directives and its handlers, and the module type, Nginx HTTP module in this case, denoting it's an HTTP-related module. This setup is essential for Nginx to recognize and correctly integrate the custom module into its processing pipeline. Integrating Nginx with content management systems, e.g. WordPress. Integrating Nginx with a content management system like WordPress involves configuring Nginx to properly serve the dynamic and static content of the WordPress site. This includes setting up rewrite rules for permalinks, handling PHP processing via fast CGI, and optimizing static file delivery. In the provided Nginx configuration, the listen directive tells Nginx to listen on port 80 for incoming connections. Server name specifies the domain name of the WordPress site. Root directive sets the document root where WordPress is installed. The index directive specifies the priority order of index files. The first location block uses try files to serve existing files directly or redirect to WordPress's index.php for non-existing URLs, pretty permalinks. The second location block handles PHP files, passing their processing to PHP FPM via the fast CGI pass directive, and specifies the socket or IP port of the PHP processor. The third location block optimizes the delivery of static files such as JavaScript, CSS, and images by setting their expires header to max, meaning they should be cached indefinitely by browsers. This setup ensures efficient handling of both dynamic and static content, important for WordPress sites. Community resources and support. Navigating through Nginx's vast landscape can sometimes require guidance beyond official documentation. This is where community resources and support come into play. They offer insights, shared experiences, and innovative solutions from various corners of the world. This Nginx configuration snippet is an example of a common solution found in community forums for handling 404 errors gracefully. By checking if the request matches an existing file or directory and returning a 404 error if none are found, it demonstrates how community-sourced solutions can enhance your Nginx setup. While simple, it illustrates the value of community resources in solving practical problems.